I'd like to introduce our speaker for today. We are very privileged to have with us Professor Richard Borcherds. Richard did his undergrad right here in Trinity, and he stayed here to do his PhD, supervised by John Conway. After his PhD, he introduced the idea of vertex algebra, which he then used in 1992 to prove Monstrous Moonshine, an important theorem relating monster group to modular functions. And this was conjectured by Conway and Simon Norton a decade earlier. For this work, Professor Borcherds was awarded the Fields Medal in 1998. Since then, he has moved to UC Berkeley, where he's a professor currently, and he has worked on applying these ideas of his earlier work to quantum field theory. He's a fellow of the Royal Society, of the American Mathematical Society, and the National Academy of Sciences. So today he'll be talking about some group theory. We are very glad to have you with us today, Richard.
Okay, that seems to have come up with a reasonable first slide. So this talk is going to be about the sporadic groups. So I'll start just by recalling what a group is. So a group is a collection of symmetries of something, and symmetries of something are, well, that's sort of what makes things look pretty. So here are some examples of things with various symmetries. So for example, we have here a flower with some sort of eightfold symmetry, and diamonds are considered nice, possibly because they have various symmetries. And here we see a potato, and potatoes are not generally regarded as very artistic objects. And as you can see, a potato has very little symmetry. Down at the bottom, we've got a football, which has quite a lot of symmetries, either 60 or 120, depending on how you count them. We recall what a group is. So it's just a collection of symmetries of something. So for example, if you take a tetrahedron, it's got 12 symmetries because it's got 4 faces, and you can, so there are 4 ways to map some face to the bottom. Once you put a face on the bottom, there are then 3 ways to twist it. So there are altogether 12 symmetries. Similarly, a cube has 24 symmetries, unless it's some sort of Rubik's cube, in which case its symmetry group is very much bigger, because you can also twist the faces. So just recall from the group theory course, a number of elements in a group, which is the number of symmetries, is called its order. So for instance, the symmetries of a tetrahedron has order 12. And you also need the order of an element of a group is the number of times you have to repeat it to get back where you started. So for example, if we rotate a tetrahedron by fixing one of the vertices, if we do that 3 times, we get back to where we started. So that element is order 3. A fundamental problem in group theory is to find all groups. And obviously, this is hopelessly difficult. You can at least start by finding all finite groups, and you might try and find all finite groups of a given order. And there can be more than one sort of group of a given order. So for example, if you take order 4, there are 2 different groups, and I've sort of drawn pictures of them on this slide. So at the top, there's a lot of objects with a symmetry group, which is one of the groups of order 4. This is the Klein 4 group. And you see, if you take a rectangle, you can either flip it along a horizontal axis, or you can flip it along a vertical axis, or you can rotate it by 180 degrees, or you can do nothing. So it's got 4 symmetries. And all these other objects also have 4 symmetries. If you look at the bottom of the slide, you have various other objects with 4 symmetries, because these ones you can rotate by 90 or 180 or 270 degrees. And you can see these 2 groups are different because they've got different numbers of elements of order 2. For instance, all the groups on the top half all have 3 elements of order 2, and the groups on the bottom half have only 1 element of order 2. So we have 2 different groups of order 4. So here's a puzzle for you. If you take a tennis ball, it's actually got a symmetry group of order 4. And so the question is, which of these 2 symmetry groups of order 4 does a tennis ball have? So I'll leave that as something for people to think about. Slightly unexpected answer is, what is the set of symmetries of an apple? And you might think it's got an infinite number of symmetries because you can rotate it, but if you cut it in half, you find it's got this funny sort of five-fold symmetry. It's actually got 5 seed pods arranged like this. And if we allow reflections as well, it's got 10 symmetries, because we can either do nothing, or there are 2 different sorts of rotations by 1/5 of a revolution, or we can have 2 rotations by 2/5 of a revolution. And there are 5 symmetries where you just reflect in a line. For instance, you might reflect in this line here. And there are obviously 5 of these. So it's got 10 different sorts of symmetries. And these 4 classes of symmetries are called the conjugacy classes. So roughly speaking, a conjugacy class of a group is a set of collection of symmetries that sort of look the same in some sense. There's another group of order 10, which is just the rotations of a 10-gon. And you can see these 2 groups are different, because this one, whoops, this one here, what's it doing that, has 4 symmetries of order 10, whereas the symmetries of an apple has no symmetries of order 10. So there are at least 2 groups of order 10. And you can continue this and ask, for each small order, how many groups of that order are there? And there's always at least 1 group of any given order, because you can take an n-sided figure. For instance, for order 7, you can just take a 7-sided polygon and just look at its group of rotations. It's sort of not quite clear what the symmetries of a 7-sided polygon are, because you could either just look at rotations, or you could look at rotations and reflections. So you get a group of order 7 and a group of order 14. But there's at least 1 group of every order. And you find, well, we've shown there are 2 groups of order 4. There are 2 groups of order 6, because we can have rotations of a hexagon, or rotations and reflections of a triangle. There are 5 groups of order 8, which I'm not going to write down because they're a little bit complicated. And you can go on to ask, how many groups are there of higher order? And the answer is there are rather a lot. So if we go to order 64, for example, there are 267 groups of order 64. These were classified by Hall several decades ago, before computers. There are this ridiculously large number of groups of order 2 to the 10, which were classified by computer. So you might think the number of groups of given order really increases really fast with the order of the group, but it doesn't, because if you look at groups of order 1,000,000, there's only 1 group of that order. It turns out, sorry, 1,000,003, never mind. So the number of groups of order n doesn't really depend very much on the size of n. It depends very much more on the number of primes and the prime factorization of n, and it depends even more on what the highest exponent of some prime is. So here we've got a if the order is divisible by some prime to the power of 10, then that means there are going to be a absolutely incredibly large number of groups. Anyway, the conclusion is that there's no reasonable way to classify all groups of order n. There are just too many of them, and they're just a confusing mess. So, for example, if we look at one of the groups of order 64, we can ask what its subgroups look like. And here is a sort of picture of its subgroups. So the subgroups of this particular group of order 64, all of order 1, 2, 4, 8, 16, 32, or 64. So here we have the group of order 64. Here are some of the subgroups of order 32 and order 16 and order 8 and order 4 and order 2. And so you can see that the structure of these groups can be quite incredibly complicated. This is worked out by hand. In fact, Hall worked out the subgroup structure of every one of the 267 groups of order 64 by hand and drew these rather amazing pictures of them. So the question is, how can you study groups? And this was sort of the first idea for doing this was done by Galois, who is rather famous for dying at the age of 21 when most of us are just doing our undergraduate exams. You know, he managed to do something that made him famous for the rest of time before most of us had done anything at all. Anyway, Galois came up with this idea that you could divide groups into basic groups that are called the simple groups. So roughly speaking, some groups can be kind of split up into smaller groups, and the ones that can't be split up into smaller groups are called simple groups. The name simple group is not very good. The groups aren't really simple at all, but we're stuck with it. So an analog of simple groups is to compare them with chemical elements. So if you're trying to classify all chemicals, you obviously can't possibly classify all chemicals. So for example, here is a typical chemical. It's a piece of a DNA molecule, and as you see, it's incredibly complicated. And there is simply no way you can possibly understand all possible chemicals. So what chemists do is they discovered that every chemical is built out of elements, and you can at least find all possible elements. So here's a collection of all known elements, which, come to think of it, needs some updating because they haven't named a few of the ones at the bottom. So the connection between groups and simple groups is just like the connection between compounds and elements. We can't classify the compounds, but we can classify the elements they're made of, and we can't classify finite groups, but we can at least classify the simple groups that they're made of. In fact, here's a picture of the simple groups. There's this guy called Ivan Andrus who, as a sort of joke, arranged all the known, all the finite simple groups into a table resembling the periodic table. It turns out that the number of the simple groups can be classified into some infinite families and some left over, and the number of infinite families just happens to be the number of columns of the usual periodic table. This is just a meaningless coincidence. I mean, the groups are arranged like this just as a joke. There's no real significance to it. So this is a sort of picture of all the finite simple groups. So here's one example of one of the finite simple groups. So first of all, there are some rather uninteresting finite simple groups, which are just the cyclic groups of prime power order. The first simple group that isn't of prime power order is the group of rotations of an icosahedron. So here's a collection of objects with that symmetry group. So this one is actually a virus. I was trying to find a picture of a coronavirus to be on topic, but as far as I can tell from pictures of coronaviruses don't seem to have icosahedral symmetry, but quite a few of them do. This one's a molecule of Buckminster fullerene, and this one here is a reflection group which actually is order 120, but if you take the subgroup of the rotations of this reflection group, it's again the icosahedral group. So the icosahedral group turns up quite a lot. So here's an actual electron micrograph of a virus, if you don't believe it has icosahedral symmetry. So on the left is the actual virus. It's not entirely obvious that this is an icosahedron because it's a bit fuzzy. So what I've done on this picture on the right is I put a white spot on each vertex of the icosahedron. So you can see this vertex this vertex and this vertex all form a little triangle. And here's a picture of the virus drawn a bit more clearly. So if you look very carefully, these circular things you can see on the left aren't actually atoms. They are molecules that make up the envelope of the virus. There's some rather clever molecule that assembles itself into icosahedra. This thing here is a little animal called a radiolarian, and here are some more pictures of them. There are some absolutely stunning pictures of these drawn by this guy called Haeckel, who drew these very famous pictures of various animals and plants. So here are some of his pictures of radiolarians. They have this little skeleton made out of calcium carbonate, I think, and these skeletons are often in the form of icosahedra or something like that. And, you know, I've often thought that, you know, maybe, you know, there are some people who like to bash evolution, saying how on earth could various things possibly evolve? And they don't seem to have thought of radiolarians, because it's a rather puzzling question. How do you evolve an icosahedron? I mean, you know, evolution normally works by making small changes in order to get something. It's very hard to see how you can make small changes to something and end up with an icosahedron. I mean, what are you going to do? Have a skeleton that consists of 17 triangles? I mean, it sounds kind of ridiculous. So I've no idea how these radiolarians managed to evolve these icosahedral skeletons. So the question is, how do you classify the finite simple groups? And here's a picture of the classification. The classification is the longest and most complicated proof in mathematics, at least the longest that has been actually written out in journals. There are some much longer proofs whose proofs consist of computer calculations, but those don't really count. So this pile of books here is roughly most of a proof of the classification. And as you can see, it's several feet high. So here's the conclusion of the classification of simple groups. First of all, there are 18 infinite families of groups and 26 left over called the sporadic groups, which are what I'm mainly going to talk about. So typical examples of simple groups are the cyclic groups that I mentioned earlier, and the icosahedral group of order 60. Some examples of the sporadic groups. The smallest sporadic group is the Mathieu group, M11 of order 7920. And the largest of the sporadic groups has been named the monster group. And the reason for the name is pretty obvious if you look at its order, which is somewhere around 10 to the 54. It's more than the number of atoms making up the planet Earth, if you want to get some idea of the size of this group. So here are some examples of the infinite families of simple groups. First of all, the cyclic groups, which are the obvious ones. The next family of simple groups that most people come across are the alternating groups. So the alternating groups are almost the same as the symmetric groups. So the symmetric groups is just the group of all permutations of n objects. So the symmetric group is order n factorial. And it's not quite simple, but it has a simple subgroup of order 2 called the alternating group. So this is simple provided n is at least 5. The alternating groups of order for any 1, 2, 3, or 4 elements are not simple. Another typical family of infinite simple groups is a general linear group, at least if you ignore the fact that this isn't quite simple. So the general linear group consists of all matrices, n by n matrices over FQ, which is the field of Q elements, where Q is a prime power. And it's not difficult to work out its order. Its order is given like this. It's not quite simple because in order to get a simple group, you first have to take the subgroup of elements of determinant 1 and then quotient out by the center. And if you do this, you get a group called PSL2 FQ. The P stands for projective, which means quotient out by the center, and the S stands for special, which means take determinant equal to 1. So the groups PSL N of FQ are simple, except they're sometimes not, because there are 2 exceptions. And this gives you some hint of why the classification of simple groups is so complicated, because there are exceptions to almost everything. So the groups PSL NFQ are simple, except there are these 2 exceptions, and these 2 exceptions have to be dealt with somewhere in the proof. And there are exceptions all over the place turning up in classification, all of which make the proof longer and longer, because you have to have separate arguments dealing with all the different exceptional cases. Well, as well as the general linear groups, you can form analogues of things like orthogonal or unitary or symplectic groups. So any group you can define over the real numbers, in other words, a Lie group, has a sort of analog over finite fields, and that gives you some of the infinite families of simple groups. So the question is, how do you find all the simple groups? So here's a very rough outline of the proof. So here I'm compressing about 10,000 pages of complicated argument into 3 or 4 lines. So obviously I'm going to miss out a few of the details. The absolutely fundamental idea of the classification is due to Brouwer, who suggests you classify simple groups by finding the possible centralizer of an involution. So an involution of a group is an element of order 2, and the centralizer is the things that commute with it. And the way the classification works is that you first of all find all possible centralizers of involution, and for each centralizer of involution you find the simple groups with that centralizer. Well, in order to start off the classification, you've got to show that every non-cyclic finite simple group has at least 1 involution, otherwise you can't get started. I missed out the word non-cyclic down here, so it's not true that every finite simple group has an involution. And the start of the classification is usually dated to this theorem by Walter Fite and John Thompson, saying that every finite simple group has an involution. And this theorem is the scariest theorem in mathematics I know about. And let me show you why it's scary. I'm going to show you their proof. Let me see. Okay, here we have the classification of simple groups of odd order by Walter Fite and John Thompson. So here their paper is called Solvability of Groups of Odd Order. And this paper takes up an entire issue of the journal, so it's about 250 pages long, and it is amazingly scary. Let me show you some of the bits of it. So let me try and zoom in a bit. So here, for example, we have a definition somewhere in the middle, and the definition starts up here and goes on down here and covers a fair amount of the next page as well. So we have definitions that are more than a page long. If I go to a later part of the proof, let's look at this page here. So this is a bit of the proof of one of the following lemmas. So you can see the proof consists of defining these weird numbers here, and we have this incredibly complicated calculation. I have no idea what is going on in this calculation. And just onto a few lines of this sort of calculation goes on and on and on for several pages. I have just no idea how Walter Fite and John Thompson managed to think of this proof. Now, the problem is that, well, so, you know, when I see a proof in mathematics, a difficult proof, I normally think to myself, well, you know, I could have found that proof if I'd worked a bit harder. But the solvability of groups of odd order by Fite and Thompson, I just can't fool myself. there is no way I could possibly have found that proof, no matter how long I've worked. So let's see if I can get back to my slides. So that is the proof by Feit and Thompson that every finite simple group has an involution, right? That is, maybe 200 pages. The full proof of the classification is maybe 50 or 100 times longer than that paper by Feit and Thompson. And quite a lot of it is just as difficult and as complicated as the proof by Feit and Thompson. So we have 10 or 20,000 pages of impenetrably complicated arguments to classify the finite simple groups. So let's give an example of a little piece of a proof. So one particular possible centralizer of an involution might be a group of order 2, that's C modulo 2Z, times the group PSL2 of FQ. That's more or less 2 by 2 matrices over a finite field of order Q. Now, if Q is a power of 3, the groups with this as a centralizer of an involution turn out to be one of the more obscure infinite families called the Rie groups. So there are an infinite number of them. If Q is anything other than a power of 3, you usually get nothing, with one exception. If Q is equal to 4 or 5, then you get a new simple group of order 175560. This was a very famous group discovered by Janko in the early 60s, and it caused a sensation because it was the first new sporadic simple group that had been discovered for almost a century. I mean, people have been discovering a lot of groups that are similar to Lie groups over the reals, and we're hoping that was all of them, but then Janko upset everybody by finding this group. The first sporadic groups to be discovered were actually discovered almost a century earlier by this guy Mathieu. These groups are called M11, M12, M22, M23, M24, where the M stands for Mathieu, and the numbers 11, 12, 22, 23, and 24 come because these groups are groups of permutations on 11 or 12 and so on points. So for example, M11 acts as permutations on a set of 11 points and has order 7,920. If you want to see an explicit description of M11, it's not terribly difficult. We can take these two permutations. So this permutation here is just a cyclic permutation that takes 1 to 2, 2 to 3, 3 to 4, and so on. Whereas this is a permutation that takes 3 to 7, 7 to 11, 11 to 8, 8 to 3, and then takes 4 to 10, 10 to 5, and so on. And if you take all permutations you can obtain by multiplying these two together, you get the group M11. So it's not difficult to define M11, although as you see, this definition by two permutations doesn't really give a whole lot of insight into the group. You have to do a lot of calculation to see what's going on. Similarly, M12 has order 95040. It's actually an example of something called a five-fold transitive group. For any 12 points, sorry, for any 5 points, there's a unique element of M12 taking those 5 points to any other 5 points you choose. So that's why its order is 12 times 11 times 10 times 9 times 8. You can actually describe M12 explicitly as a sort of sliding block puzzle fairly easily. If you take the projected plane of order 3, it has 13 lines and 13 points. And it's order 3 because each line has 4 points. I guess somebody miscounted when they were figuring out what the order was. But what you can do is you can put 12 counters on 12 of these 13 points. And you have a sort of sliding block puzzle where you're allowed to move any counter to an, you're allowed to slide it along one of the lines to another, to an empty point. But whenever you do that, you have to switch the other two counters on that line. And if you do that, you get a sort of sliding block puzzle. And M12 consists of the all permutations you can get by sliding things around that leave the empty point in the same place. So now I want to talk about a rather famous simple group discovered by John Conway. John Conway found this by looking at a certain sphere packing. So you can ask the question, what is the densest way you can pack spheres in some given number of dimensions? Well, one-dimensional sphere packings are kind of trivial. 2 dimensions, you can pack them on a sort of square grid like this, if you like. And that's obviously not the best possible packing. You can pack them more tightly by packing them hexagonally. So in 3 dimensions, this was actually a problem that the British Navy worried about because they wanted to store cannonballs in the most efficient possible way. So they actually got some guy to figure out what the best way of storing cannonballs on a ship was. So I think this was possibly the earliest study of sphere packing. There are actually several ways of doing this. First of all, we can take a cubic packing. So you might take something like a salt crystal, and they're packed in a cube. And this is obviously not the best sort of packing. There are 2 obvious dense packings. First is one called face-centered cubic, where the spheres are arranged like this. There's also something called a hexagonal close packing. So here's an example of hexagonal close packing. So what's the difference between face-centered cubic and hexagonal close packing? Well, suppose you take a hexagonal layer. So all these white circles are going to be the lowest layer of spheres. And then you can put on a second layer of spheres, which are these black ones. And then it turns out there are 2 ways to put a third layer of spheres. Whoops, because you can put the third layer so they're either above the first layer, like this one here. And if you do that, you get hexagonal close packing. And if you put them so they're different from the layer that's 2 below, you get a face-centered cubic. So you can think that there are actually 3 ways to put the spheres in each layer. You can put them in positions A, or positions B, or position C. And face-centered cubic, you sort of put the successive layers A, B, C, A, B, C, and so on. Whereas hexagonal close packing, you put them in layers A, B, A, B, A, B, and so on. In fact, there are an uncountable number of other equally dense ways, because you can choose any collection of letters with no 2 consecutive letters, and that gives you a dense packing. For instance, you can pack them like A, B, A, B, C, A, B, A, B, C, and so on. So there are an uncountable number of equally dense packings in 3 dimensions. So obviously you can ask, what is the best sphere packing in various dimensions? And in dimension 1, this is trivial. In dimension 2, it's easy. In dimension 3, face-centered cubic is the densest possible packing, although it's not unique. And this is incredibly difficult to prove, as I'll mention in a moment. In dimensions 4 to 7, we haven't managed to prove what the answer is. I mean, we sort of think we know the answer, but we can't prove it. In 8 dimensions, we have managed to find the densest packing. This is something called the E8 lattice that I'll describe a little bit later. In dimensions 9 to 23, we're not sure what the answer is. In dimension 24, we know the densest possible packing. It's something called the Leech lattice. And in dimension greater than 24, we don't know. So this is very weird. You would have thought that the next most difficult case after dimension 3 was dimension 4, but we don't know how to solve it in 4 dimensions. You have to jump to 8 and 24 dimensions. So something very bizarre is going on in dimensions 8 and 24. So the proof of the best sphere packing in 3 dimensions was done by Thomas Hales in 1998. This was the Kepler conjecture. And this is one of the longest proofs in mathematics. It's far longer than the classification of finite simple groups, but it cheats because it uses computers. And so the proof consists of several terabytes of computer data. So if you wrote it all out, it would be vastly bigger than the classification of finite simple groups. the fact that E8 is the densest packing in 8 dimensions was proved by Marina Vyazovska in 2016, who came up with this absolutely stunning proof of it. This was an extension of some work by Henry Cohen and Noam Elkies, who showed that E8 would be the densest 8-dimensional sphere packing, provided you could find a certain magical function with certain rather bizarre properties. And quite a lot of people tried to find such a function. I spent a few hours on it and got absolutely nowhere. And Marina Vyazovskaya managed to come up with this absolutely incredible way of constructing such a function. I must admit, I tried to understand her argument and can't really figure out what's going on. So how do we describe the sphere packing in 8 dimensions? Well, the easy way to describe a sphere packing is to give the coordinates of the centers of its spheres. So if I want to describe the usual cubical packing like this one here, I can just say the centers are all numbers ABC with ABC integers. And you can see there are 6 spheres touching a given sphere. For face-centered cubic, the centers consist of all numbers ABC whose sum is even. And then you can see there are these 12 spheres all touching the sphere at the origin. For E8, you do something similar. You take, these numbers must either all be integers or they must all be integers plus a half. So for example, these vectors here are all in the lattice packing, and again the sum must be even. And now you can see there are 240 touching the sphere at the origin because there are 128 vectors like this. You might think there are 256 because there are 8 choices of sign, but in fact the sum has to be even, so that cuts things down by a factor of 2. And then there are 8 times 7 times 2 vectors of this form, so that gives you another 112 spheres. So altogether we have 128 plus 112 spheres touching the sphere at the origin, which is 240. So we've got an arrangement of 240 spheres in 8 dimensions, and here's an attempt to draw a picture of it. This is the 240 spheres in 8 dimensions, except they've been projected down into 2 dimensions. So, and there's a line drawn between 2 of the spheres in, if they're touching each other in 8 dimensions, you get this rather complicated picture here. The automorphism group of the E8 lattice is actually a reflection group. So a reflection group is a group of symmetries of Euclidean space or a sphere generated by reflection. So here are some examples of reflection groups. So the first 3 are just Euclidean reflection groups. You see that there are lots of reflections that preserve these patterns. For instance, if you reflect along this line here, it preserves this triangular pattern, only it exchanges black and white diagrams. And similarly, this is another reflection group. These 3 spheres at the bottom are examples of spherical reflection groups. You see, you can reflect in these great circles. For instance, there's a great circle here at the bottom. And this gives you 3 spherical reflection groups. And you can also get reflection groups in hyperbolic space, which I'm not going to talk about much, but here are a couple of examples. So on the top right here, we have a sort of model of the hyperbolic plane, and these are in fact triangles with straight edges, and the reason these edges look curved rather than straight is they get a bit distorted because we're working with hyperbolic space rather than Euclidean space. Anyway, so this example here and the example here on the bottom left give you examples of hyperbolic reflection groups. So here's so the E8 reflection group, the symmetries of the E8 lattice is actually a reflection group, and you can describe it explicitly because it's just generated by 120 reflections, which are reflections in the hyperplanes orthogonal to the 240 vectors giving you the centers of spheres. You can think of this as in 3 dimensions. The analog would be that the symmetries of a cube are generated by reflections, giving you a reflection group that looks like this. You're reflecting in these great circles. So the reflection group of the E8 lattice is sort of similar, but lives in 8 dimensions rather than 3 dimensions. Now we get to the symmetry group of the Leech lattice in 24 dimensions that was investigated by John Conway. This is a picture of John Conway demonstrating, well, one of the things he was most proud of was that his tongue was more flexible than the tongue of anybody else he ever met. And he claimed he could do some very large numbers of weird patterns with his tongue, and here he is demonstrating one of them. Anyway, among mathematicians, he's actually best known for the Conway group, which can be thought of as a symmetry of a sphere packing. So here we have a sphere packing in 2 dimensions, and it's got 12 symmetries because you can rotate it or reflect it. In 3 dimensions, it's not difficult to figure out that this sphere packing is 48 symmetries. In 8 dimensions, we get this E8 sphere packing, and the number of symmetries is this large number here. In 24 dimensions, every sphere touches 196560 other spheres, and the symmetry group was worked out by John Conway, and he got this rather impressive number. And this was particularly exciting because this symmetry group was more or less a new sporadic simple group. You have to sort of quote it out by center order 2, but anyway. So John Conway said, you know, this was sort of made him world famous, and he went around the world giving lectures on this new group, and actually found 3 different groups because there were 3 new ways of getting sporadic groups out of the Leech lattice. So how do you construct the Leech lattice? Well, let's go back to this question. Ask, how many cannonballs are there in a pile? Well, the top layer has 1 cannonball, the next layer has 2 squared, the next layer has 3 squared, and so on. So the total number of cannonballs is 1 squared plus 2 squared up to n squared. And now you can ask the apparently silly question, can we find a pile of cannonballs like this such that the total number of cannonballs is a square? And apart from the trivial solution when there's only 0 or 1 cannonballs, there's only one solution. You have to have 24 layers, and there are 70 squared cannonballs. And we can use this to construct the Leech lattice. What we do is we start with 26-dimensional Lorentzian space. What this means is it's like Euclidean space, except the distance is defined in a funny way. You have a minus sign in front of one of the variables. So if you've done special relativity, you've come across this, except in 4 dimensions. It's just called Lorentzian space. And you can sort of define distances in the usual way, except that sometimes distances are imaginary because this number here might be negative, and that gives you time-like vectors and so on in special relativity. Anyway, I'm going to take the following vector W, which is 70, 0, 1, 2, up to 24. And the key point is that W has length 0 because the sum of the first 24 squares is 70 squared. So now we're using this weird fact that if you've got a pile of cannonballs with 24 layers, it has a square number of cannonballs. And now we can use this norm 0 vector W to form the Leech lattice as follows. What we do is we take all vectors such that the coordinates are integers or half integers, and the sum of the coordinates is even. So this is exactly what we did for constructing the E8 lattice. And now we take all vectors orthogonal to W, and we should actually divide out by W as well, but I won't worry about that. And that gives you the Leech lattice. So the Leech lattice in 24 dimensions depends on this rather weird fact that the sum of the first 24 squares is a square. And Conway's group is the group of symmetries of the Leech lattice. Obvious question is, can you do something like this in any other number of dimensions? And the answer seems to be no. This is something weird that only happens in 24 dimensions. For the rest of this talk, I want to explain John Mackay's T-shirt. So John Mackay is a Canadian mathematician, and he had a special T-shirt custom made pointing out his great discovery that 196883 plus 1 is equal to 196884. And let me explain what the significance of this is. 196883 is the dimension of a representation of the monstrous simple group, and 196884 is a coefficient of an elliptic modular function that I'll explain later. And John Mackay pointed out these two numbers only differed by 1, and most people dismiss this as being a meaningless coincidence. So if you get a large number of numbers, you can find weird coincidences between them. For example, e to the pi minus pi is very, very close to 20. And as far as we know, there is no significance to this. It's just this meaningless coincidence. And John Mackay, when he put out this, was told by several people that this was just another meaningless coincidence. The explanation involves something called the elliptic modular function. Sorry, I skipped a slide. Another apparently weird coincidence is if you take e to the pi times root of n, then these numbers here are often very close to being integers. So here are 3 examples. They aren't always. For instance, if you take e to the pi times the square root of 1, this is e to the power of pi. And this is 23, which isn't nearly an integer. It's very nearly 20 plus pi, but as far as I know, there's no good reason for that. Anyway, so what's going on here? Why are these numbers here very nearly integers? Well, the explanation involves Klein's elliptic modular function. So here's a picture of Felix Klein, and here's a picture of his bottle, which he's most famous for. By the way, it wasn't originally called a bottle. It was originally called Klein's surface, but the German words for surface and bottle look very much the same, and I think some translator got a bit confused between them. So actually, apparently, although it was originally called a Klein surface in German, even the Germans have now started calling it a Klein bottle. But anyway, so here's Klein's elliptic modular function. It looks like a really bizarre definition for a function. I mean, if you look at this definition here, it looks like someone wrote it down as a sort of silly joke. You can work out its power series expansion, and it looks like this. So here's this number 196884 that appeared on John Mackay's T-shirt. And what's the point of this function? Well, it turns out to be the simplest non-constant function that has the following 3 properties. So it's invariant under taking tau to tau plus 1, and it's also invariant under taking tau to minus 1 over tau. Functions invariant under tau to tau plus 1 are very easy to define. These are just periodic functions, and they're just Fourier series, and e to the 2 pi I tau has period 1. So any function of q will satisfy the first equality. It's the second equality that's very difficult to arrange, and this really does turn out to be the simplest solution. So here's a picture of the graph of Klein's elliptic modular function. Well, it's actually a slightly different elliptic modular function. So what's going on here is that this is the upper half plane in the complex numbers. So down here we have the real axis, and you see along the real axis there's this whole chain of poles where the function becomes infinite. And if you go away from the real axis, the function becomes very small. So it's, as you can see, it's a really complicated function. By the way, this picture has only drawn a few of the poles for simplicity. That there are really an infinite number of smaller and smaller poles getting denser and denser along the real axis. So you should really think of them as there's just a wall of poles, not just a finite number of them. So now we can explain why these numbers like e to the pi root 163 are almost integers. Well, Klein's elliptic modular function is given like this. And if you take q to be the number e to the minus pi root 163, then the elliptic modular function is exactly an integer. The reason for this comes from a mathematical theory called complex multiplication, and the integer turns out to be 640320 cubed. On the other hand, the number 1 over q is approximately e to the pi root 163, which is this number up here. This number is an integer, and this term here, 1968884q, turns out to be incredibly small. I mean, you might think it's rather big because 1968884 is big, but it turns out that q is so small that all these terms here are incredibly tiny. So the result is that e to the pi root 163 is very nearly this integer here, plus 744. Anyway, now we should talk about the monster group. So the monster group is the largest of the sporadic simple groups. So the icosahedral group lives in just 3 dimensions and has 60 symmetries. Conway's group lives in 24 dimensions and has this number of symmetries. The monster group lives in 196883 dimensions. This is the other number appearing on John Mackay's t-shirt, and its number of elements is given by this number here that I'm not going to read out explicitly. So it was discovered by Fischer and Griess in the early 70s. Or rather, Fischer and Griess at first suggested the possibility of a group like this existing, but for a long time it was unclear whether there was such a group, because it's actually incredibly difficult writing down such a group. I mean, what are you going to do? Write down matrices that are 196883 by 196883? They would have about 1 billion entries. I mean, it's you know, you can't write them down and calculate with them. Well, you couldn't with the computers at that time. Well, its existence was originally proved by Robert Griess, who actually managed to more or less write down explicitly matrices in this number of dimensions. I remember I was at Cambridge when this proof came out, and when Robert Griess managed to announce he'd constructed this group, people at Cambridge basically could almost not believe it, because you know they'd known it was possible in principle to construct the group by acting as matrices in 196883 dimensions, but assumed the calculations would be so phenomenally difficult that no one could possibly do them. But Robert Griess spent several months working really, really hard on this problem and managed to come up with this paper that was well over 100 pages long, where he showed how to construct suitable matrices constructing this group. His construction has since been simplified quite a lot, but it was a really incredible construction when it came out. Anyway, so you can look at the monster character table. Now, the character table of a group tells you what dimensions it can live in, and here is a very tiny piece of the monster character table. So we can see this entry here is a 1, and here's 196883, which is the smallest dimension it lives in, and it also lives in 21296,876 dimensions, and so on with all these numbers. The full table actually has about 194 rows and 194 columns. So I've just shown you the top 9 or 10 rows of it. Anyway, if you remember, the elliptic modular function had these coefficients, and it turns out the coefficients of the elliptic modular function are very closely related to the entries in this column of the monster character table. These are the dimensions the monster can live in. So the first row we get 196884 is 196883 plus 1. Well, if that was the only information you had, you might write it off just as a meaningless coincidence. However, the next coefficient is equal to the sum of the first 3 dimensions of representations of the monster. And the next coefficient is also equal to a simple linear combination of dimensions of the monster. And at this point, you can no longer say this is just some sort of meaningless coincidence. So how can you explain this? Well, John Thompson suggested there should be an infinite dimensional graded vector space acted on by the monster, such that the dimensions of its various pieces were given by these coefficients. And this was constructed by Frenkel, Lepowski, and Merman in the early 1980s. So we've got a vector space V, which is a sum of finite dimensional pieces Vn, and the dimension of each space Vn is one of the coefficients of J. I should say that you have to sort of throw away this number 744. The elliptic modular function is only defined up to an arbitrary constant, and this number 744 only occurs for historical reasons. There's no great significance to it. So you throw it away, and all the other coefficients are coefficients of Frenkel, Lepowski, and Merman's algebra. So this graded vector space is actually related to string theory. So you remember we constructed the Leech lattice by taking a 26-dimensional Lorentzian space and then fiddling around with it. Well, 26-dimensional Lorentzian space is not that much use for physics because we live in a 4-dimensional Lorentzian space, not a 26-dimensional one. However, one of the more promising approaches to high-energy physics is string theory, and the early versions of string theory only worked in 26 dimensions. And this is a bit of an embarrassment for physicists working on string theory because you know, we don't live in 26 dimensions. However, it's although physicists are not very happy, 26 dimensions is very nice for mathematicians because the 26 dimensions of string theory turn out to be exactly what you need for dealing with the Monstrous simple group and the Leech lattice. So Frenkel, Lepowski, and Merman's construction of this graded vector space in the monster action, in fact, uses things called vertex operators coming from string theory. And again, there's something called a no-ghost theorem in string theory you need in order to get things working properly, which only works nicely in 26 dimensions. So that all works for the Monstrous simple group. It's got a graded vector space whose coefficients are dimensions of weird functions. You can ask, does something similar happen for the other sporadic simple groups? And the answer is, it does for some of them. For instance, another of the groups Fischer discovered is called the baby monster group. In fact, Fischer discovered this before he found the monster group, and he found the monster group by suggesting the baby monster group, or rather a double cover of it, should be the centralizer of an involution in the monster group. Anyway, if you look at the baby monster group, it lives in dimensions 1, 4, 3, 7, 1, 9, 6, 3, 5, 5. Sorry, that should be a 2 there. That's a misprint. 9, 6, 2, 5, 5, and so on. And there's a more complicated version of the elliptic modular function whose coefficients look like this. And you can see this coefficient 4372 is very close to this coefficient 4371. And similarly, all the other coefficients of this function are related to representations of the baby monster group. And many of the other sporadic simple groups are also related to elliptic modular functions in a similar way. There are, however, some variants of this that haven't been explained yet. So if you want to do some, try some research that isn't understood yet, we can take a mock theta function. So mock theta functions were introduced by Ramanujan in one of his letters to Hardy just before he died. And one example of a mock theta function has Fourier coefficients that look like this. On the other hand, if you take the Mathieu group M24 that we discussed briefly earlier. It lives in dimensions 23, 45, 231, and so on. And now if you look at these coefficients, 45, 231, 770, 2277, they're the same as these numbers, 45, 231, 770, 2277, and so on. And nobody knows why. So there are quite a lot of other variations of this connecting M22 to various lattices in 24 dimensions called Niemeyer lattices. So it's clear that this is not just a coincidence, but no one has really come up with a good explanation for it. You can ask, is there some sort of algebraic structure like a vertex algebra underlying it? Well, maybe, but it's a bit difficult because this coefficient here is -1, which means you would need a -1 dimensional vector space, which is a little bit hard to deal with. So we have an open question. Why do these numbers turn up in two different places? I just finished with a sort of philosophical question. Why do sporadic groups exist at all? I find this absolutely bizarre because if you look at the axioms for a group, they're completely trivial. You can write them out here and they're just half a line long and they're very natural and simple. And somehow the monster group and all the complexity of the classification of finite simple groups is hidden inside these almost trivial axioms. So we can ask, is there some sort of uniform explanation of the sporadic groups? You know, why do the sporadic groups exist at all? Is the classification really that complicated, or are we missing some fundamentally simple approach to the classification which would explain what's going on? So I think I'll just finish there just by leaving a few suggestions of further reading. So if you want a popular book on the monster and sporadic groups, there's one by Ronan. If you're feeling really ambitious and want to find out what's really going on, then two good sources for this: the book by Conway and Sloan on sphere packings, lattices and groups that describes the Leech lattice in detail. And if you want a survey of the finite simple groups, there's a very nice book by Daniel Gorenstein on finite simple groups. Okay, I think I'll stop there and answer any questions that the audience has.
Okay, yeah, thanks a lot. This was really interesting. Yes, yeah, now we have some time for questions. And I think I'll start off with one kind of related to what you're talking about at the end. Do you have any intuition at all as to why the number of sporadic groups is finite?
No,
okay.
No one has. This was a question people were discussing in the 1960s, because most of the sporadic groups were discovered in the 1960s and the 70s, and people kept finding more of them. And there was a lot of speculation about whether there were a finite or an infinite number of them. For instance, when the Yanko group J1 was discovered, it looked a bit as if it was the first of an infinite family of new groups. So people tried rather hard to find more groups like it, but never managed to come up with any. And no one has ever come up with a good reason why the number of sporadic groups is only finite. The only explanation for it is 20,000 pages of the classification of finite simple groups, where you just show by brute force that there aren't any others.
Yeah, thank you. Does anyone else have any questions? Yes. You can put them in the chat, or you can ask them out loud.
Could I ask something?
Sure.
So, like you said at the start, groups are the study of symmetry in a way. So do you find it unsatisfying that the classification is so unsymmetric, and you know, does it bother you in that way?
Well, it does sort of annoy me that it's too complicated for me to understand. I mean, I sort of, the trouble is, it's kind of obvious that even if I devoted the rest of my life working 8 hours a day trying to understand the classification, I'd never be able to do it. And it's just simply too difficult. My supervisor, John Conway, on the other hand, had the opposite attitude. He was kind of disappointed that the simple groups had been classified and thought it'd be much nicer if there were an infinite number of sporadic groups, so we would never get to the end of them.
So is there a reason we specifically tunneled on groups, or do you think there could be similar classifications of monoids or more complicated structures in groups?
Well, finite simple groups seems to be the absolute limit of what we can reasonably classify. So if you try weakening the axiom slightly, like going to semigroups or monoids, you seem to get such an awful mess that there doesn't seem to be any sign of a useful classification. On the other hand, there are some related things like Lie algebras over finite fields, and people have sort of classified these. The problem is that nothing terribly interesting turns up. You don't get any analogues of sporadic groups. You mostly just get known infinite families plus a few odds and ends that don't seem to do very much. So I think this was a bit of a disappointment to people, because a lot of techniques were developed for classifying finite groups, and these techniques just don't seem to be useful for anything else in mathematics. So they're going to be just forgotten because, there's nothing else to do with them.
Here's a question I got from someone. Do you expect the proof of the classification to become simplified in the future? Or are people just going to leave it alone and say it's done? We can move on to more interesting things.
Some people are working on the classification. The original proof can certainly be simplified and shortened quite a bit, because when it was originally developed, people didn't know what they were doing and had proved things in ways that could later be simplified quite a lot. So there is a revised calculation by Gorenstein, Lyons, and Solomon, I think, gradually being published. I think they published 7 of a projected 12 volumes, but it's still several thousand pages long and not easy reading. Whether or not there's a fundamentally simpler classification that an ordinary person could understand in their lifetime, I don't know. People have sort of wondered if there is some fundamentally different way of classifying groups, but no one has ever come up with any plausible way of doing this. So maybe it really is that complicated.
Can I ask if you have a particularly favorite simple group of your own?
Well, I guess the monster, since that's the one I worked on most, or maybe just because it's the biggest one. The ones that I'm most familiar with are either the Monster or Conway's group of symmetries of the Leech lattice. I guess those two would count as my favorites.
Thank you.
I was going to ask, is there a particularly satisfying construction of a monster group? Because I've seen John Conway's simplification of the Griess algebra constriction.
Yes,
it seems rather piecemeal, as in it constructs it from below almost in a quite hodgepodge manner.
This is an open research question for anyone who's interested. Find a natural construction of the monster. Every construction of the monster we have is a mess. Most of the constructions are essentially simplifications of Griess's original construction. And the problem with all of them is you take two huge vector spaces which seem to have nothing to do with each other. You take their direct sum and you put some sort of piecemeal algebra structure on this, and by some amazing fluke, it just happens that the monster is a group of automorphisms. We don't have a, I mean, you would never find this construction unless you already suspected the monster existed and were trying to construct it. What we would really like is a sort of one-piece construction where you construct it just as in one piece. For instance, Conway's group, you take the Leech lattice in 24 dimensions, and that's a very natural single object in 24 dimensions. We don't have anything like that for the monster yet.
I noticed that like you used the Heegner numbers, I believe, in when you're describing like how each, like you're showing how that also showed up in the elliptic curve. So I wondered if like other Heegner numbers also showed up using the...
Yes, all the Heegner numbers that are discriminants of imaginary quadratic fields show up that e to the pi times the square root of something is very nearly an integer.
So those would also fall under the, as in the monster group as well, or would they be two like smaller groups, as in, or is it just...
Sorry, there was a bit of interference. I didn't quite catch your question.
So the question was like, so would those smaller numbers refer to like smaller groups, or would they also fall under this monster group like relationship?
I don't think the Heegner numbers are directly connected with the monster group. They're just indirectly connected because both the monster and the Heegner numbers are related to the elliptic modular function. But I don't. I mean, the Heegner numbers don't really correspond to anything in the monster group by themselves.
Wait, so there's a few more questions from the chat. Yeah, so first of all, just a comment from Gareth Taylor saying that he remembers you lecturing modular forms back in 1997. He says it was his favorite part 3 course. And since then we have a question asking, so now that we have classified finite simple groups, does this mean that in some sense we have classified all the finite groups, or do you not really know what?
Not really, because this is like the question, if you've classified the elements, have you classified all chemical compounds? And obviously not, because the ways you can stick elements together are just so complicated that you can't really classify all compounds just knowing the elements. And we have the same problem with finite groups, that the ways you can join together finite simple groups to make a finite group are just too complicated to classify. I mean, even if you just take copies of the finite simple group of order 2, the simplest possible finite simple group, and take a dozen of those, then it seems to be, just explain how you can join those together seems to be almost too complicated to describe. So no, we can't really classify all finite groups, even knowing the simple ones. There is no simple, and I can answer the other question. So someone has asked, is there a simple answer to how do we know there aren't any more sporadic groups? Actually, I think I just answered this a little bit earlier. The answer is there is no simple answer to why there are no more sporadic groups. The only answer is 20,000 pages of the classification.
Can I quickly ask away? Okay, so quick question that isn't so much about the talk, but the people who you spoke about. So in some of our lectures, we always heard fun stories about Conway doing weird and odd things. Do you have any fun stories of Conway's oddities?
Well, there was the time he built a computer out of toilet components. I think he once explained to us that if you look at the flush mechanism of a toilet, it's really a sort of logical gate, because you pour water in, and once the water gets up to a certain level, it gives an output. And he claimed that he once built a computer using these, and he said it was exhibited in the Guildhall in Cambridge or somewhere like that, but they never invited him back because it had a some sort of overflow and caused a certain amount of damage to the flooring. I guess it makes the concept of an overflow in computing rather more dramatic than the usual meaning. I have a sort of suspicion that he made up or exaggerated some of the stories he told about himself, though, so I take this with a grain of salt.
Okay, yeah, thank you very much. That's fun to hear.
Yeah, that was a great story. Thanks. Does anyone else have any more questions?
You have mentioned sphere packing related to sporadic groups. So I want to ask if tessellations in general, are they related to classification of groups or?
Well, yeah. I mean, tessellations are very similar to sphere packings. I mean, if you've got a sphere packing, you can get a tessellation out of it, and if you've got a tessellation, you can quite often get a sphere packing. So you can regard the Leech lattice as being a tessellation of 24-dimensional space, for example.
Yeah,
do you mean for every tessellation we have a sphere packing?
Well,
or we have a sphere packing.
I'm not saying there's a one-to-one correspondence. I'm just saying that they're very closely related to each other. So if you've got a tessellation, you can quite often get a sphere packing.
Cool. Thank you very much.
So I have another question, just kind of on the most basic level. How does any of this relate to any of the physics? So, yeah, how does this relate to string theory or the quantum field theory? Why is any of this related?
There's no short, easy answer to that. The Frenkel-Lepowski and Merman used things called vertex algebras, vertex operators in their construction of the monster. And a vertex operator in string theory is roughly something that tells you what happens when two strings are interacting and producing a third string. So the word vertex actually comes from the vertex of a Feynman diagram. So whether or not string theory is related to physics is a rather controversial question. I mean, physicists seem to be have been arguing rather emotionally for several decades about whether string theory is really physics or not. So I have to leave that question open. But certainly, I mean, although even if it's not directly related from physics, there are some ideas that go backwards and forwards. I mean, the vertex operators in string theory are quite similar to the vertices of Feynman diagrams in quantum field theory.
Yeah, thank you. Yeah, and here's another question that I got from someone. So what's the relation to error correcting codes? If there's any relation.
Well, actually, I think one of the books I mentioned at the end was a book by Thompson on error correcting codes and lattices. The relation to error correcting codes, well, there are several relations. First of all, you can use error correcting codes to construct lattices. So for instance, the Leech lattice was originally constructed using an error correcting code. The construction I gave using 1 squared plus 2 squared and so on equals 70 squared was only found later. And there are other sporadic groups that can be constructed directly from error correcting codes. For example, the Mathieu group M24 is the group of symmetries of an error correcting code called the Golay code, which is a 12-dimensional subset of a 24-dimensional space over the field with 2 elements. For more on this, see the book by Conway and Sloan, which gives into much more detail.
Okay, thanks a lot. Does anyone else have any more questions?
Yes, I was going to ask, this is returning to the monster group. Towards the end of the Conway paper, there was a remark that Simon Norton had constructed a lattice inside the Griess algebra by taking, I think, integer linear combinations of axes of transposition vectors, but I couldn't find anywhere else in the literature anything about this particular lattice. I was just wondering whether or not it's been investigated in greater detail anywhere.
Yes, I think such a lattice may have been constructed recently by Carnahan, if I've remembered correctly. I think Simon Norton's lattice wasn't quite unimodular, but I think a unimodular lattice has now been constructed. Quite a lot of Simon Norton's things were never actually published, so this is a common problem. Yeah, if you look at papers by Scott Carnahan on the archive, you may come up with something about this lattice.
Thank you very much.
Thanks. Any more questions? Right, well, if there aren't any more questions, yeah, let's all just say thank you to Professor Richard Borcherds. It was a really interesting talk. Yeah, thanks a lot. Yeah, I learned a lot. It was great to hear from you. Yeah, and so thank you to everyone for coming. It's great to see so many people here. This is going to be the last talk of this term.